Welcome to a brand new episode of Physics with Friends. I'm the physics guy. I'm gonna run a course in string theory and related topics, but before we do that, since this is the first ever video published on my channel, I'd like to say a few words about my profile picture and the banner. Well, as we can see, there are two geometrical objects here. First one is a thinking diagram of SO8. Well, I choose it because not only does it enjoy a property known as triality, which has something to do with its three inequivalent reducible representations, well, eight-dimensional representations. The fundamental one, obviously, and its two spinal representations. It also appears in the context of superstring theory. Well, as we all know, that physical Maxwell states belong to representations of SO2 in four-dimensional Minkowski spacetime. And in terms of superstring theory, the spacetime dimension is 10. So naturally, physical Maxwell states belong to representations of SO8 in superstring theory. And the next object is a torus. Well, strictly speaking, a two-torus, commonly known as a donut. Well, just for the record, I didn't pick it because I want to tone some vice presidential candidate. I put it here because I think it's special. Well, I mean, in topology, it is a very basic example illustrating the concepts like homology group or homotopy group. And in differential geometry, it is compact complex manifold. Well, even more, it is a compact Calabi-Yau one-fold, and it's also the building block of the only two types of compact Calabi-Yau two-fold, namely T4, which is a direct product of two tori, and K3, the orbifold limit of which could be T4 modulo Z2. It also appears in our discussion on modular invariance and fundamental regions, so I think it's fairly important. But string theory, is a highly complicated field. We can usually see a lot of beautiful interplay between mathematics and physics in string theory. So not only should we appreciate it from geometrical points of view, it is important as well to study it through an algebraic lens. So that is the reason why I threw some formulas here. The first one is renowned Virasoro algebra, which is important in determining the coupling constant and the spacetime dimension in both bosonic strings and superstrings. The second one is the string action, in RNS formalism of superstring theory. The first term is obviously, the good old action for Messenger scalars, and the second one is just the action for spinors. And the third one is a definition of Ricci form. I put it here because I want to emphasize the importance of complex geometry in in string theory. The cohomology class of Ricci form is proportional to the first Chern class, and the vanishing of which is virtually the defining property of Calabi-Yau manifold. And the latter appears extensively in literature, so I think it's worth noting here. All right, and this is my email address. Discussions of any topic, including but definitely not limited to physics, would be welcomed. Okay, so without further ado, or as in this case with enough further ado, let's get started. I'd like to start with an introduction of myself and some stories behind my own physics study. And some features of this course will be provided, like how it's going to be structured, what are the prerequisites, and in the end, I'd like to wrap it up with why I decided to make a video series on string theory. So currently, I am about to enter the third year study in college, and I am not a physics student. Well, don't leave now. Well, it's not because of this. To justify which, I think it's necessary to list my physics learning history. I was the type of guy who dabbles a lot. because I am a curious person, probably. Back in high school, I studied biology and I went participating in biology Olympiad, and I was in school track team. And in college, I majored in geosciences. Well, in a sense, I still do. And I audited a lot of courses ranging from sociology, history, even French history taught in French, to mathematics. I always want to become a scientist, but was just unclear on which field. Until one day I went to a lecture on cosmology, and the lecturer was talking about Friedman equation, like if you accept the universe is isotropic and homogeneous, then you get Friedman-Robinson Walker magic. And if you also accept Einstein's field equation, then by plugging in the magic, you get the Friedman equation, which is arguably the most important equation in cosmology. But back then, I didn't know anything about general relativity, so I didn't know what Ricci tensor, Ricci scalar, or even edge momentum tensor is. But I was like, wow, that was pretty cool. And that is how I started learning general relativity myself. And it's also how I decided to do physics in the future. But as a serious physics student, I just I got a feeling that it is a must to learn quantum mechanics. Well, largely because that's a part of physics most perceived by the society or by the public. Like basically everyone knows about Schrodinger's cats, and well, in public's opinion, they are like well, quantum mechanics is some weird stuff about uncertainty. So I started learning that as well. And also I read a book on cosmology at that time. And in the following semester, I began to systematically take courses in physics. As you can see here, I took most of the courses required for physics students to take. It was a time when I realized I was not condensed matter physics material, because I wasn't as interested in many body systems as I was in high energy physics. Well, that was also part of the reason I started reading some books on particle physics, especially the one written by David Griffith. But back then, I virtually knew nothing about group theory. So, well, to extent that I didn't even know why there are only 8 types of gluons instead of Li in QCD. And after learning physics for about a year, I started learning quantum field theory. Well, because back then there was a teacher publishing course online talking about it, and he talked about how to canonically quantize scalar fields, vector fields, and spanner fields. That was my initial encounter with Clifford algebra, with Feynman propagators, with like basic tree-level calculations in QED, like how to write down invariant amplitude by simply looking at Feynman diagrams. And he even talked about some fancy stuff like LSA reduction formula or optical theorem. Well, the former is useful for converting endpoint correlators calculated by path integral to asymmetric management, which is directly related to the observables. But oddly enough, he didn't talk about path integral nor renormalization, both of which play an essential role in QFT calculations. So I bridged the gap by reading this book myself, which is written by Professor Matthew Schwartz at Harvard. And that was also around the time when I started learning string theory. I read some lecture notes published online, but I wasn't just mathematically prepared to read it. Like I didn't know much of the math required to tackle string theory back then. So I remember feeling perplexed by concepts like BRST cohomology class. Because in string theory there is an equivalent description for physical states, which is BRST cohomology class with certain Gauss number, which is conventionally taken to be -1/2. Well, it's just a choice. We'll talk about it in the following lectures. But back then I just knew very little stuff about this field. And then I bought a book. I bought this book written by Professor Sweebach at MIT, and I read it in winter vacation. If you didn't have any encounters with string theory before, I strongly recommend this book. As I record, this book is intended for third-year students in college, so I don't think you're gonna have any trouble following the reasoning and demonstration of this book, because it's very detailedly written. And after finishing reading this book, I did a presentation on ADS-CFT correspondence. Well, it was nothing like those highbrow presentations you would expect to see in, say, string conferences, because I really am just a student. It was a fairly introductory presentation on ADS-5CFT correspondence, which is the first of its kind, first propounded by Juan Maldacena back in the 19s. And it's a correspondence between type 2B superstring theory and four-dimensional n=4 super-Young Mills. After that presentation, I took some questions from the audience, namely the students, my classmates. And some of the questions were about string theory. My answers were far from perfect because I seemed to get some facts wrong, but was still fantastic because, standing on the podium, talking about string theory as if you'd know it for a long time, that was just amazing. And I think that sort of motivated me to keep exploring the glory of this field. And I always knew that I am really lacking in the basic mathematics to understand this field, let alone tackling real problems in this field. So as well as learning string theory further, I studied some books on mathematics required by string theory. And it's like I spent the first 3 months reading all the books I'm gonna use in this course, and the other 2 months rereading those books and preparing for this course, like making the PowerPoint. So this is about the 2-year saga of my physics learning history, and I think it naturally brings us to the next topic, which is the structure of this lecture, of this course.